Imagine hurtling through the cosmos, past swirling galaxies and shimmering nebulae, on a journey to find a new home among the stars. Our destination? Earth-like worlds nestled in the habitable zones of distant solar systems. These are places where the temperature is just right, where water could flow, and where life, as we know it, might thrive. We're not talking about science fiction here, but a scientific quest that's very much underway. In this video, we'll embark on a virtual voyage to these tantalizing exoplanets, exploring their landscapes and revealing the cutting-edge science that brings us closer to answering one of humanity's oldest questions: are we alone in the universe? Understanding the habitable zone. In the vast, frigid expanse of space, the concept of a habitable zone is akin to a cozy, life-sustaining oasis. This zone, often referred to as the Goldilocks zone, is a region around a star where the temperature is just right for liquid water to exist on the surface of a planet. Not too hot, not too cold, but just right, much like the porridge in the classic fairy tale. This delicate balance is crucial for life as we know it, as water is a fundamental ingredient for life on Earth. The habitable zone is not a fixed distance from a star, but rather a dynamic region that shifts based on the star's size, brightness, and the planet's atmospheric composition. For instance, a planet orbiting a smaller, cooler star would need to be closer to maintain the necessary temperatures for liquid water, while a planet orbiting a larger, hotter star would need to be farther away. The habitable zone is not a guarantee of life, but rather a starting point for scientists in their search for Earth-like worlds. It provides a framework for identifying potentially habitable planets among the thousands discovered in recent years. However, the habitable zone is not the only factor to consider. A planet's atmosphere, geology, and magnetic field also play crucial roles in its habitability. For example, a planet might be within the habitable zone, but if it lacks a substantial atmosphere, any liquid water on its surface would quickly boil away or freeze. Similarly, a planet with a strong magnetic field can shield its atmosphere from being stripped away by stellar winds, increasing its chances of retaining a life-sustaining environment. Consider the stark contrast between the inner and outer reaches of our own solar system. Mercury, the closest planet to the Sun, is a scorched, airless world where any water would have long since evaporated. In contrast, Mars, while farther from the Sun, is cold and dry, with any remaining water locked away in its polar ice caps and possibly beneath its surface. Earth, however, sits comfortably in the middle, with a temperate climate that allows for vast oceans, lush forests, and a diverse array of life. This is the sweet spot that scientists are hoping to find around other stars, a place where the conditions might be just right for life to thrive. The search for Earth-like worlds within the habitable zones of other stars is an exciting and rapidly evolving field of study. With each new discovery, our understanding of the universe and our place within it grows. The journey to the habitable zone is not just a physical one, but a scientific and philosophical one as well, as we grapple with the implications of finding life beyond Earth. It's a journey that inspires awe and wonder, as we peer into the depths of space and contemplate the possibilities that lie within the habitable zones of distant stars. Defining Earth-like worlds. In the vast, frigid expanse of space, where stars twinkle like distant lighthouses, the concept of Earth-like worlds emerges as a beacon of hope for humanity's future. These planets, often nestled within the habitable zones of their respective stars, are the cosmic equivalents of Earth's diverse ecosystems. They orbit at just the right distance to allow for the existence of liquid water, a crucial ingredient for life as we know it. Scientists often refer to this sweet spot as the Goldilocks zone, where conditions are neither too hot nor too cold, but just right for life to potentially thrive. Picture the lush rainforests of the Amazon, the vast oceans teeming with marine life, or the arid yet resilient deserts of the Sahara. Earth-like worlds could mirror these environments, offering a tantalizing glimpse into the possibility of extraterrestrial life. The search for Earth-like worlds has intensified with the advent of advanced telescopes and space exploration technologies. NASA's Kepler Space Telescope, for instance, has identified thousands of exoplanets, some of which exhibit characteristics reminiscent of Earth. These planets vary in size, composition, and atmospheric conditions, but they share a common thread: the potential to harbor life. Consider the planet Proxima Centauri b, which orbits the closest star to our solar system. Despite its proximity to a red dwarf star, it lies within the habitable zone, sparking speculation about the possibility of liquid water on its surface. The journey to these distant worlds, while daunting, is driven by the human spirit of exploration and the quest for knowledge. Understanding Earth-like worlds involves delving into the intricate dance of planetary formation and stellar dynamics. These planets often form from the same cosmic dust and gas that gave birth to our solar system. Their atmospheres, composed of nitrogen, oxygen, and other trace gases, can create conditions conducive to life. Scientists study the spectral signatures of these atmospheres to determine their composition and potential habitability. For example, the presence of methane and oxygen in an exoplanet's atmosphere could indicate biological activity, much like the forests of Earth teeming with life. The study of Earth-like worlds not only expands our understanding of the universe, but also deepens our appreciation for the delicate balance that sustains life on our home planet. The role of stellar radiation. Stellar radiation is the lifeblood of any planetary system, dictating the very conditions that allow for the existence of Earth-like worlds. It's the golden glow of a star, a constant stream of energy that bathes planets in warmth and light. Much like the sun's rays that kiss the Earth's surface, stellar radiation is a complex interplay of electromagnetic waves, from the visible light that nourishes life to the invisible, high-energy particles that can strip away atmospheres. The intensity and composition of this radiation vary greatly among stars, shaping the environments of their orbiting planets in profound ways. For instance, a star's spectral type, whether it's a cool, red dwarf or a hot, blue giant, determines the amount and type of radiation emitted, influencing everything from a planet's temperature to its atmospheric chemistry. Consider the radiation from a star like our Sun, a G-type main-sequence star. It emits a broad spectrum of radiation, including visible light, ultraviolet, UV, rays, and 10th rays. This radiation is crucial for driving atmospheric processes and supporting life. On Earth, UV radiation, while harmful in excess, plays a pivotal role in the formation of the ozone layer, which in turn protects life from harmful cosmic rays. Similarly, the visible light from the sun powers photosynthesis, the process by which plants convert light energy into chemical energy, forming the base of the food chain. However, not all stars are as benign. Some, like the active M-type red dwarfs, emit intense flares and high levels of UV and 10th ray radiation. These flares can strip away a planet's atmosphere over time, making it difficult for life as we know it to thrive. This is a stark reminder that while stellar radiation is essential, its intensity and variability can be a double-edged sword. The habitable zone, often referred to as the Goldilocks zone, is the region around a star where the stellar radiation is just right, not too hot, not too cold, for liquid water to exist on a planet's surface. This zone is not a fixed distance, but varies depending on the star's type and age. For example, a red dwarf's habitable zone is much closer to the star than our Sun's, due to its lower luminosity. However, the increased radiation and flares from these stars can make the habitable zone a more hostile environment. In contrast, a larger, hotter star like a blue giant has a habitable zone that's much farther out, but the intense radiation and shorter lifespan of such stars can also pose challenges for potential life. The interplay between stellar radiation and a planet's atmosphere, geology, and magnetic field is complex and dynamic, making the search for Earth-like worlds a fascinating and multifaceted endeavor. Understanding the role of stellar radiation is not just about finding habitable planets. It's also about understanding the limits of life itself. For instance, some organisms on Earth, like certain species of bacteria and algae, thrive in extreme environments with high levels of radiation. These extremophiles offer tantalizing clues about the potential for life in seemingly inhospitable environments around other stars. Moreover, studying stellar radiation helps us understand the evolution of our own solar system and the factors that have made Earth a haven for life. It's a reminder that we are not just passive observers in the cosmos, but active participants in a grand, ongoing experiment of life and its possibilities. Planetary atmospheres and climate. The vast expanse of space is not just a cold, empty void. It's a tapestry of diverse worlds, each with its own unique atmospheric symphony. Planetary atmospheres are crucial players in the quest for habitable zones, acting as protective blankets that regulate temperature, shield from radiation, and support life as we know it. Take Earth, for instance. Our atmosphere is a delicate balance of nitrogen, oxygen, and trace gases, creating a greenhouse effect that keeps our planet warm and cozy. Without it, Earth would be a frozen wasteland, much like Mars, where the thin atmosphere offers little protection from the harsh cosmic elements. Consider the thick, soupy atmosphere of Venus, a runaway greenhouse effect gone wild. It's a stark reminder of how a planet's atmosphere can dramatically alter its climate. The surface temperature is hot enough to melt lead, with crushing atmospheric pressure. Yet, just above the cloud layers, temperatures and pressures are almost Earth-like. This is why scientists are so fascinated with planetary atmospheres. They're not just blankets. They're dynamic systems that can create pockets of habitability even in the most unlikely places. Now, let's talk about atmospheric composition. It's not just about the gases present, but also their proportions. Earth's atmosphere is about 78% of nitrogen and 21% of oxygen, with trace amounts of other gases like argon, carbon dioxide, and water vapor. These trace gases play a significant role in regulating our climate. For example, carbon dioxide, though present in small amounts, is a potent greenhouse gas that traps heat and keeps our planet warm. On the other hand, Mars' atmosphere is about 95% of carbon dioxide, with only trace amounts of oxygen and water vapor. This stark difference explains why Mars is a frozen desert while Earth is a lush, blue marble. Atmospheric pressure is another critical factor. It's the force exerted by the atmosphere on the planet's surface. Earth's average atmospheric pressure is about 14.7 pounds per square inch at sea level. This pressure is just right for liquid water to exist on the surface, a crucial ingredient for life as we know it. In contrast, Mars' atmospheric pressure is only about 0.6% of Earth's, far too low for liquid water to exist on its surface. This is why any water on Mars is either frozen in the polar ice caps or hidden beneath the surface. Understanding these atmospheric dynamics is key to identifying potentially habitable worlds. It's not just about finding Earth-like planets. It's about finding planets with the right atmospheric conditions to support life. The Goldilocks principle. In the vast, frigid expanse of space, where temperatures plummet to hundreds of degrees below freezing, the concept of a habitable zone might seem like a distant dream. Yet, nestled within the harsh void, there exists a delicate band of space where conditions are just right for life as we know it. This is the habitable zone, often likened to the Goldilocks zone. Not too hot, not too cold, but just right. It's a region around a star where the temperature is tempered enough for liquid water to exist on the surface of an orbiting planet. Earth, of course, is the prime example, comfortably nestled within our sun's habitable zone. But as we venture out into the cosmos, we're finding that other stars have their own Goldilocks zones, and within them, Earth-like worlds that could potentially harbor life. Consider the planet Kepler 442b, a rocky world orbiting a star much like our own. It's located about 200 light-years away, but in the grand scheme of the universe, that's a mere stone's throw. Kepler 442b receives about 70% of the sunlight that Earth does, placing it firmly within its star's habitable zone. Its year is longer than ours, about 112 Earth days, but its temperature is likely within the range where liquid water could exist. It's a stark reminder that habitable zones aren't just theoretical constructs. They're places where life could potentially thrive. The Goldilocks principle extends beyond just temperature. It's about finding that perfect balance of conditions. Take, for instance, the planet Proxima Centauri b, the closest known exoplanet to our solar system. It orbits within the habitable zone of its star, Proxima Centauri, a red dwarf. However, the planet is likely tidally locked, meaning one side perpetually faces its star while the other is shrouded in eternal night. This creates a stark contrast, with one side scorching hot and the other freezing cold. Yet, in the twilight zone between these two extremes, There could be a region where temperatures are just right and liquid water could exist. It's a testament to the complexity of the Goldilocks principle and the intricate dance of factors that make a planet habitable. As we continue our journey to the habitable zone, we're not just looking for Earth-like worlds. We're searching for the conditions that make life possible. It's a journey that takes us from the familiar to the utterly alien, from the comfort of our own solar system to the far-flung reaches of the cosmos. And as we go, we're reminded that the Goldilocks principle isn't just about finding a place that's just right. It's about understanding the delicate balance that makes life possible and the incredible diversity of worlds that could harbor it. Key characteristics of Earth-like planets. In the vast, cold expanse of space, Earth-like planets are the cosmic oases that beckon us with the promise of life beyond our home. These planets, often nestled within the habitable zone of their stars, share several key characteristics that make them tantalizing targets for exploration. They orbit stars similar to our Sun, receiving just the right amount of warmth to allow for liquid water to exist on their surfaces. This is the first and most crucial ingredient for life as we know it. Think of it like the Goldilocks story. Not too hot, not too cold, but just right. These planets are often rocky, with a solid surface where water can pool and life can take root. They have atmospheres, too, which act like a cozy blanket, trapping heat and protecting the surface from harmful radiation. Earth's atmosphere is a delicate balance of nitrogen, oxygen, and other gases, and we're finding that Earth-like exoplanets often have their own unique atmospheric recipes. The size of these planets is another critical factor. They're not too big, like gas giants such as Jupiter, and not too small, like Mercury. This Goldilocks size allows for a surface where liquid water can exist and where a stable climate can be maintained. It's like finding the perfect sized pot for your stew. Too big, and the flavors won't melt. Too small, and it'll boil over. Earth-like planets also have a magnetic field, an invisible force field that protects the planet from solar winds and cosmic radiation. This magnetic field is generated by the planet's molten core, a dynamic dance of liquid metal that creates a protective bubble around the planet. Without it, life as we know it wouldn't stand a chance. Then there's the matter of geology. Earth-like planets are geologically active, with plate tectonics that recycle materials and create a dynamic surface. This geological activity is crucial for maintaining a stable climate and creating the right conditions for life. It's like a planet-wide recycling system, constantly renewing and refreshing the surface. Volcanic activity, for instance, releases gases that can contribute to the atmosphere, creating a complex interplay between the planet's interior and its surface. Water, too, plays a significant role in this geological activity. It can seep into the planet's crust, react with minerals, and create a rich chemical soup that could potentially give rise to life. It's a complex, interconnected system, much like the intricate web of life we see on Earth. Lastly, these planets often have moons or other celestial bodies in their vicinity. These neighbors can have a stabilizing effect on the planet's orbit and axial tilt, creating a more stable climate. They can also contribute to the planet's geological activity through tidal forces. Think of it like a cosmic dance, where each body influences the others, creating a harmonious and stable system. These characteristics, just the right amount of warmth, a rocky surface, an atmosphere, the right size, a magnetic field, geological activity, and celestial neighbors, are the hallmarks of Earth-like planets. They're the cosmic ingredients that could potentially give rise to life, making these worlds the most exciting targets for our exploration of the cosmos. Detecting exoplanets. The cosmos is a vast, dark ocean, and we are but a small island in it. For centuries, we've gazed up at the stars, wondering if there are other islands out there, other worlds like our own. Now, with the advancements in technology, we're beginning to find them. These distant planets, orbiting other stars, are called exoplanets. Detecting them is like finding a needle in a cosmic haystack, a challenge that astronomers have risen to with ingenuity and perseverance. One of the most common methods to detect exoplanets is the transit method. It's akin to observing a bird flying in front of a street lamp at night. The bird blocks some of the light, and we see a dip in brightness. Similarly, when an exoplanet passes or transits in front of its host star, it blocks a tiny amount of the star's light. This minuscule drop in brightness is what astronomers look for. The Kepler Space Telescope, for instance, has used this method to discover thousands of exoplanets. It's like having a telescope that can spot a flea crawling on a car's headlight from miles away. Another method is the radial velocity or wobble method. Stars don't stand still. They orbit around the center of mass of their planetary system. This motion causes a shift in the star's spectral lines, a phenomenon known as the Doppler effect. It's similar to how a siren's pitch changes as it approaches and then moves away from you. By measuring these shifts, astronomers can infer the presence of an exoplanet. This method has led to the discovery of many exoplanets, including some that are potentially habitable. It's like listening to the universe's symphony and hearing the faint, off-key notes that hint at hidden instruments. Direct imaging is a more recent and challenging method. It involves taking actual pictures of exoplanets. This is like trying to take a picture of a firefly next to a searchlight from miles away. The star's light is so bright that it overwhelms the planet's dim glow. To overcome this, astronomers use coronagraphs to block out the star's light. This method has allowed us to see some of the largest exoplanets, giving us a glimpse of what these distant worlds might look like. It's a testament to human ingenuity, our unyielding quest to explore and understand the cosmos. Transit method, a window to distant worlds. In the vast, inky blackness of space, where stars twinkle like distant lighthouses, astronomers have developed a remarkable technique to spy on worlds orbiting other suns. This method, known as the transit method, is akin to observing a tiny moth fluttering past a bright street lamp from miles away. It's a testament to human ingenuity and our insatiable curiosity about the cosmos. At its core, the transit method relies on the slight dimming of a star's light as a planet passes in front of it, a cosmic eclipse that betrays the presence of an unseen world. This dimming is often minuscule, sometimes just a fraction of a percent, but with sophisticated instruments and clever algorithms, scientists can detect these subtle changes. Consider our own solar system. If an alien astronomer were to observe Earth transiting the Sun, they would see a dip in the Sun's light by about 0.1%. That's a drop from 100% to 99.99%. A change so small it's akin to noticing a single grain of sand disappearing from a beach. Yet, this is the scale at which astronomers operate, using space-based telescopes like Kepler and TESS to monitor the brightness of thousands of stars simultaneously. When a transit occurs, the star's light is filtered through the planet's atmosphere, if it has one. This allows scientists to analyze the starlight and glean information about the planet's atmospheric composition, temperature, and even weather patterns. It's like reading the label on a bottle by the faint glow of a distant streetlight. The transit method has revealed a treasure trove of exoplanets, some of which reside in the habitable zone, that Goldilocks region where conditions might be just right for liquid water to exist. Take Kepler 186f, for instance, a planet orbiting a red dwarf star about 500 light-years away. It's a rocky world, slightly larger than Earth, and it receives about a third of the light that Earth gets from the Sun. While it's not a perfect twin of Earth, it's a tantalizing candidate in the search for life beyond our solar system. Similarly, TOI 700d, discovered by TESS, is another Earth-sized planet in the habitable zone, orbiting a star about 100 light-years away. These discoveries are just the beginning, as the transit method continues to push the boundaries of our understanding of the universe. The data collected from transit events is rich with information. By studying the depth, duration, and shape of the transit light curve, astronomers can determine the planet's size, orbital period, and distance from its star. Additionally, spectroscopic analysis of the starlight passing through the planet's atmosphere can reveal the presence of molecules like water vapor, methane, and oxygen, which are potential biosignatures. It's like conducting a forensic analysis of a crime scene, piecing together clues to paint a picture of a world we've never seen. The transit method is a powerful tool in our exoplanet hunting arsenal, offering a window into the diverse worlds that populate our galaxy. Each transit event is a snapshot of a planet's journey around its star, a fleeting moment that holds the promise of unlocking the mysteries of the cosmos. Radial velocity, measuring planetary wobbles. In the vast, silent ballet of the cosmos, stars are not the only dancers. Planets, too, pirouette around their stellar partners, their gravitational tugs creating a celestial waltz. This dance, though imperceptible to the naked eye, leaves telltale signs that astronomers have learned to decipher. One such method, radial velocity, measures the minute wobbles of stars caused by the gravitational pull of orbiting planets. It's akin to observing a tree sway to infer the presence of an invisible wind, or in this case, an unseen planet. The technique hinges on the Doppler effect, a phenomenon familiar to anyone who's heard an ambulance siren change pitch as it passes by. As a star moves towards us, its light shifts to bluer wavelengths. As it moves away, it shifts to redder ones. These shifts, though minuscule, can be detected with sensitive spectrographs. By measuring these changes, astronomers can deduce the presence of a planet, its mass, and even the shape of its orbit. It's a bit like listening to a symphony and deducing the number of musicians, their instruments, and the conductor's tempo from the subtle variations in the music. Consider our own solar system. Jupiter, the heavyweight among planets, causes the sun to wobble with a velocity of about 12.5 meters per second. That's a leisurely walking pace, but it's enough to be detected from Earth. Now, scale this up to distant stars. The wobble caused by an Earth-like planet in the habitable zone, a region where liquid water could exist, would be a mere 9 centimeters per second. Detecting such a subtle movement is akin to measuring the thickness of a sheet of paper from a kilometer away. Yet, with advancements in technology, astronomers are inching closer to this feat. The quest for Earth-like worlds is not just about finding a second home. It's about understanding our place in the universe. Each wobble measured, each planet discovered, adds a piece to the cosmic puzzle. It's a journey that takes us beyond the confines of our solar system, into the habitable zones of distant stars, and perhaps, one day, to the shores of alien oceans. Direct imaging, seeing the unseeable. In the vast, inky blackness of space, finding Earth-like worlds is like searching for a needle in a cosmic haystack. Direct imaging, a cutting-edge technique, is our high-tech magnet, pulling these elusive exoplanets into view. It's a challenging endeavor, akin to spotting a firefly next to a lighthouse from miles away. The light from a star, much like the lighthouse, can be billions of times brighter than the faint glow of a planet. To overcome this, astronomers use a coronagraph, a device that blocks out the starlight, allowing the much fainter light from the planet to be detected. This is similar to shielding your eyes from the sun to see something in the distance. The planets that direct imaging can detect are often young and hot, their own heat making them glow like embers in the night. These are the gas giants, the Jupiter-like worlds that orbit far from their stars, in the cold, dark reaches of their systems. But it's not just heat that makes these planets visible. Some reflect light from their stars, like a mirror catching the sun's rays. This reflected light can reveal a wealth of information about the planet's atmosphere, its weather, even its potential habitability. It's a tantalizing glimpse into worlds that, until recently, were purely the stuff of science fiction. Consider the Earth-like worlds that might exist in the habitable zones of other stars. These are the planets where liquid water could exist on the surface, where life as we know it might have a fighting chance. Direct imaging is our best hope for seeing these worlds directly, for studying their atmospheres, their surfaces, their potential for life. It's a daunting task, but one that's already yielding results. The first direct images of exoplanets have been captured, and they're just the beginning. Each image is a step closer to answering one of humanity's oldest questions. Are we alone in the universe? The journey to the habitable zone is fraught with technical challenges. The planets are small, their orbits tight, and their stars blindingly bright. But astronomers are clever, and they're developing new techniques to overcome these obstacles. They're using advanced optics to sharpen their view, like switching from a blurred to a high-definition screen. They're employing sophisticated data processing to tease out the faint signals from the noise. And they're pushing the limits of their telescopes, both on the ground and in space. Each advancement brings us closer to seeing the unseeable, to finding those Earth-like worlds that might be out there, waiting to be discovered. Gravitational microlensing, a cosmic magnifying glass. In the vast, dark ocean of space, where stars twinkle like distant lighthouses, astronomers have developed a remarkable tool to spot elusive, Earth-like worlds, gravitational microlensing. This phenomenon, predicted by Einstein's theory of general relativity, acts as a cosmic magnifying glass, bending and amplifying the light of distant stars when a massive object, like a planet, passes between them and an observer on Earth. It's akin to the way a straw appears bent or seems to shift position when viewed through the base of a wine glass. This effect is subtle, fleeting, and requires precise alignment, making it a rare but powerful tool in the exoplanet hunter's arsenal. Consider the Earth's own journey around the Sun, a predictable, elliptical dance that we've come to rely on for seasons and tides. Now, imagine a planet orbiting a distant star far beyond our solar system. As this exoplanet drifts through the cosmos, it can chance upon a perfect alignment with a background star and our own vantage point on Earth. The exoplanet's gravity warps the space around it, causing the light from the distant star to bend and brighten, like a lighthouse beam passing through a prism. This temporary brightening is the telltale sign of a microlensing event, a cosmic wink that betrays the presence of an otherwise invisible world. The beauty of gravitational microlensing lies in its ability to detect planets that other methods might miss. It's particularly sensitive to planets that orbit at a distance from their host stars, in the cold, dark fringes of what we call the habitable zone. This is the region around a star where temperatures could allow for liquid water to exist on a planet's surface, a crucial ingredient for life as we know it. Think of it like the temperate regions of Earth, where life thrives between the frozen poles and the scorching equator. Microlensing can spot these far-flung worlds, providing a more complete picture of the planetary systems beyond our own. However, microlensing events are unpredictable and brief, lasting from a few hours to a few days. This makes them challenging to study, like trying to catch a fleeting glimpse of a shy, elusive creature in the dense undergrowth of a rainforest. Astronomers must be vigilant, ready to pounce on these transient events with ground-based telescopes and space-based observatories. Yet, the effort is worthwhile. Each microlensing event offers a unique opportunity to probe the properties of distant exoplanets, from their mass and distance from their host star to their orbital eccentricity. It's a testament to human ingenuity, using the very fabric of space-time as a tool to explore the cosmos and search for Earth-like worlds among the stars. The Kepler mission, a revolution in exoplanet discovery. In the vast, dark ocean of space, the Kepler Space Telescope has been a beacon of discovery, illuminating the cosmos with its unblinking gaze. Launched with a singular purpose, it has revolutionized our understanding of exoplanets, those distant worlds orbiting stars beyond our solar system. Kepler's primary mission was to survey a portion of the Milky Way, seeking out Earth-like planets in the habitable zones of their stars, where liquid water could potentially exist. This is the region around a star where the temperature is just right for water to be in liquid form, not too hot for it to boil away, not too cold for it to freeze solid. It's the Goldilocks zone of planetary science. Kepler's approach was akin to a cosmic census taker, using the transit method to detect exoplanets. As a planet passes in front of its star, it causes a tiny dip in the star's brightness, a fleeting shadow that Kepler could detect. This method has led to the discovery of thousands of exoplanets, with many more candidate planets awaiting confirmation. The telescope's data has revealed a staggering diversity of worlds, from scorching hot planets with molten surfaces to icy giants drifting in the cold, dark depths of space. Among these, Kepler has found a number of potentially habitable planets, their sizes and orbits suggesting they could have conditions suitable for life as we know it. The implications of Kepler's discoveries are profound. For the first time, we have a statistical sense of how common Earth-like planets might be in our galaxy. The data suggests that nearly every star in the Milky Way could have at least one planet, with many stars hosting multiple planets. This is a profound shift from the view of just a few decades ago, when we weren't sure if any planets existed beyond our solar system. Kepler's findings have also challenged our notions of what a planet is and where it can form. Some planets have been found in orbits so tight that a year lasts only a few Earth days, while others circle their stars at distances that would place them in the outer reaches of our solar system. These worlds push the boundaries of our understanding and force us to reconsider our models of planetary formation and evolution. TESS, the Transiting Exoplanet Survey Satellite. In the vast, dark ocean of space, the Transiting Exoplanet Survey Satellite, or TESS, acts as a vigilant lighthouse, scanning the cosmos for Earth-like worlds. Launched with a primary mission to discover planets orbiting the brightest stars in our cosmic neighborhood, TESS is a technological marvel, a celestial cartographer charting the course to potential habitable zones. It's like a modern-day Magellan, but instead of sailing the Earth's oceans, it's navigating the boundless sea of stars, searching for new worlds that might harbor life. TESS employs a unique method to detect exoplanets, using the transit method. This involves monitoring the brightness of stars over time. When a planet passes in front of its star from our perspective, it causes a tiny dip in the star's brightness. It's akin to observing a moth fluttering past a porch light, causing a brief flicker. By measuring these flickers, TESS can infer the presence of planets, their sizes, and even the potential for habitability. This method has already led to the discovery of thousands of planet candidates, some of which are Earth-sized and orbit within their star's habitable zone. The habitable zone, often referred to as the Goldilocks zone, is the region around a star where the temperature is just right for liquid water to exist on a planet's surface. Too close to the star, and the planet is too hot, like Venus. Too far away, and it's too cold, like Mars. But in the habitable zone, conditions might be just right, like Earth. TESS's discoveries have expanded our understanding of these zones, revealing that they can be more diverse and complex than initially thought. Some planets might have elliptical orbits, spending only part of their time in the habitable zone. Others might be tidally locked, with one side perpetually facing their star, creating unique environmental conditions. TESS's data has also allowed scientists to study the atmospheres of these exoplanets, using a technique called transmission spectroscopy. When a planet transits its star, a small amount of starlight passes through the planet's atmosphere, leaving behind spectral fingerprints that can be analyzed. These fingerprints can reveal the composition of the atmosphere, including the presence of water vapor, methane, and other potential biosignatures. It's like reading the chemical makeup of a distant world, looking for clues that might indicate habitability or even life. With each new discovery, TESS brings us one step closer to answering the age-old question, are we alone in the universe? Future missions, James Webb Space Telescope and beyond. The James Webb Space Telescope, JWST, often hailed as the successor to the Hubble Space Telescope, is a marvel of modern engineering. Positioned far beyond the reach of Earth's atmosphere, it peers into the cosmos with an infrared eye, capable of detecting the faintest whispers of light from the earliest galaxies. Its primary mirror, a golden, hexagonal masterpiece spanning 6.5 meters, is composed of 18 individual segments that work in unison to capture the universe's secrets. JWST's mission is to explore the formation of the first stars and galaxies, the evolution of planetary systems, and the potential for life in the habitable zones of exoplanets. In the quest for Earth-like worlds, JWST plays a pivotal role. It can analyze the atmospheres of exoplanets, searching for biosignatures, chemical signatures that might indicate the presence of life. For instance, the telescope can detect the presence of water vapor, carbon dioxide, and methane, which are key indicators of a planet's potential habitability. Think of it as a cosmic detective, sniffing out the clues left behind by distant worlds. The telescope's sensitivity allows it to study planets that are light years away, providing a glimpse into environments that might mirror Earth's. Beyond JWST, the future of space exploration is brimming with promise. Upcoming missions like the European Space Agency's Aerial, Atmospheric Remote Sensing Infrared Exoplanet Large Survey and NASA's Habitable Worlds Observatory are set to build on JWST's legacy. Aerial, for example, will focus on characterizing the atmospheres of exoplanets, aiming to understand their composition, weather, and potential habitability. It's like having a weather satellite for alien worlds, helping us predict the conditions on planets we've never set foot on. These missions will not only expand our knowledge of the universe, but also bring us closer to answering one of humanity's most profound questions. Are we alone? The journey to the habitable zone is not just about finding new worlds. It's about understanding our place in the cosmos. Each mission, each telescope, and each discovery brings us one step closer to unraveling the mysteries of the universe. It's a journey that combines the thrill of exploration with the rigor of science, a journey that reminds us of our insatiable curiosity and our unyielding spirit of discovery. As we venture further into the cosmos, we carry with us the hope of finding a second Earth, a place where life might have taken root among the stars. The habitability of Mars, a case study. Mars, the fourth planet from the Sun, has long captivated human imagination as a potential second home. Its dusty, rust-colored surface, crisscrossed by ancient river valleys and towering volcanoes, presents a stark contrast to Earth's lush landscapes. Yet, beneath its harsh exterior, Mars holds secrets that hint at a past where liquid water flowed freely, and perhaps life might have thrived. The planet's thin atmosphere, composed mostly of carbon dioxide, offers little protection from the sun's radiation or the cold, making its surface an inhospitable place for humans. However, recent discoveries have revealed that Mars may still harbor liquid water beneath its surface, fueling hopes for potential habitability. The search for life on Mars has been a driving force behind numerous missions. Rovers like Curiosity and Perseverance have traversed the Martian landscape, analyzing soil samples and searching for signs of past or present life. These robotic explorers have found evidence of ancient lakes and streams, suggesting that Mars once had a more Earth-like climate. The presence of methane in the Martian atmosphere, detected by the Curiosity rover, has added to the intrigue, as methane on Earth is often produced by biological processes. However, it's important to note that methane can also be generated through geological processes, so its detection doesn't definitively prove the existence of life. One of the most promising regions for potential habitability is the polar ice caps. These vast expanses of ice, composed of water and carbon dioxide, hold a significant portion of Mars' water supply. Beneath the ice, there may be pockets of liquid water, kept from freezing by the planet's internal heat. These subsurface lakes could provide a refuge for microbial life, shielded from the harsh surface conditions. Moreover, the ice caps offer a valuable resource for future human explorers, providing a source of water for drinking, growing crops, and even producing rocket fuel. To make Mars truly habitable for humans, significant technological advancements are needed. Terraforming, the process of deliberately modifying a planet's environment to be more Earth-like, has been proposed as a long-term solution. This could involve releasing greenhouse gases to thicken the atmosphere and warm the planet, or introducing genetically engineered microorganisms to produce oxygen and break down toxic soils. However, these ideas remain speculative and would require centuries, if not millennia, to implement. In the meantime, human explorers would need to rely on advanced life support systems, radiation shielding, and perhaps even underground habitats to survive on Mars. The journey to the habitable zone of Mars is fraught with challenges, but the potential rewards, both scientific and inspirational, make it a journey worth undertaking. Venus, a cautionary tale. Venus, often dubbed Earth's sister planet due to their similar sizes, spins in a relentless, sun-scorched dance around our star. Yet, this proximity to the sun has rendered it a hell's cape, a stark reminder of the delicate balance that sustains life on Earth. The surface temperature averages a blistering 464 degrees Celsius, 867 degrees Fahrenheit, hot enough to melt lead. This inferno is shrouded beneath a thick, toxic atmosphere composed primarily of carbon dioxide, with clouds of sulfuric acid blanketing the planet. The atmospheric pressure is crushing, about 90 times that of Earth's, akin to the pressure found a kilometer beneath our oceans. This extreme environment makes Venus a cautionary tale, a glimpse into a world where a runaway greenhouse effect has spiraled out of control. Picture Earth, but with a twist. Venus might have once been a more hospitable place, with oceans and a climate more akin to Earth's. However, a catastrophic event, possibly a massive volcanic outburst, triggered a runaway greenhouse effect. The oceans boiled away, and the water vapor in the atmosphere contributed to further warming, creating a vicious cycle. This is a chilling reminder of the fragility of our own planet's climate. The polar ice caps, the vast oceans, the lush forests, all could be at risk if we're not careful. Venus serves as a stark warning, a planet where the balance tipped, and life as we know it became impossible. The journey to Venus is a testament to human ingenuity and our unyielding curiosity. Spacecraft like NASA's Magellan and the European Space Agency's Venus Express have braved the harsh conditions to study the planet. They've mapped its surface, analyzed its atmosphere, and even peered beneath the clouds using radar. These missions have revealed a world of extremes, with mountains, volcanoes, and vast plains. Yet, despite these efforts, Venus remains one of the least explored planets in our solar system. The extreme conditions have made it challenging to place long-term probes or rovers on the surface. However, future missions are in the works, aiming to unlock the secrets of this enigmatic world. Understanding Venus is not just about unraveling the mysteries of another planet. It's about looking into a potential future for Earth. The study of Venus's atmosphere and climate can provide valuable insights into the processes driving climate change on our own planet. By understanding what went wrong on Venus, we can better appreciate the delicate balance that sustains life on Earth. It's a humbling perspective, a reminder of our place in the cosmos, and the responsibility we have to care for our home planet. After all, Venus is a stark reminder that not all Earth-like worlds are created equal. Super-Earths and Mini-Neptunes, expanding the definition. In the vast, star-studded canvas of our universe, astronomers have discovered a menagerie of planets that defy our Earth-centric definitions. Super-Earths and Mini-Neptunes are two such categories that have expanded our understanding of what a planet can be. Super-Earths are rocky worlds with masses greater than Earth's, but smaller than ice giants like Neptune. Mini-Neptunes, on the other hand, are gaseous planets with masses smaller than Neptune's, but larger than Earth's. These planets challenge our notions of habitability and planetary formation, inviting us to reconsider the cosmic conditions that might nurture life. Picture a planet where the gravity is stronger, the days longer, and the landscapes more dramatic. Super-Earths, with their robust gravitational pull, could have atmospheres thick with clouds, perhaps laced with exotic compounds that scatter sunlight into hues unseen on Earth. The surface might be a tapestry of towering mountains and deep valleys, sculpted by the planet's intense gravity. Some super-Earths orbit within the habitable zones of their stars, where temperatures could allow for liquid water. Yet, their environments might be vastly different from Earth's. For instance, the planet LHS 1140b, a super-Earth located about 49 light-years from Earth, is thought to have a dense atmosphere and possibly a global magma ocean, painting a picture of a world in a state of intense geological activity. Meanwhile, Mini-Neptunes present an entirely different scenario. These planets are enveloped in thick hydrogen-helium atmospheres, with possible layers of high-pressure ice and a solid core. Unlike the rocky super-Earths, Mini-Neptunes might not have a solid surface at all, making them more akin to a dense, gaseous soup. The planet K2-18b, located about 124 light-years away, is a prime example. It's a mini-Neptune with a temperature range that could allow for liquid water within its atmosphere. Scientists have even detected water vapor in its atmosphere, sparking debates about its potential habitability. Yet, the high pressure and lack of a solid surface make it an unlikely candidate for life as we know it. The discovery of these planets has forced astronomers to broaden their definitions and reconsider the ingredients for life. Super-Earths and Mini-Neptunes exist in a gray area, challenging our understanding of planetary formation and habitability. They remind us that our solar system is just one example among countless others, each with its own unique cast of characters. As we continue to explore these distant worlds, we're not just expanding the boundaries of our knowledge, we're redefining the very nature of planetary science. The role of water in habitability. Water, the elixir of life, is not just a component of habitability, but its cornerstone. In the vast, cold expanse of space, where temperatures can plummet to -270 degrees Celsius, water's unique properties become a beacon of hope for life. It's a universal solvent, capable of dissolving a wide range of substances, facilitating the chemical reactions necessary for life as we know it. On Earth, water covers about 71% of the surface, creating a dynamic interplay between land and sea that has given rise to an astonishing diversity of life forms. In the search for Earth-like worlds, scientists look for this same vital ingredient, scanning distant exoplanets for signs of water's telltale spectral signature. The role of water in habitability extends far beyond its chemical properties. It acts as a temperature regulator, absorbing and redistributing heat, creating stable climates conducive to life. Consider Earth's oceans, which can absorb vast amounts of heat, mitigating temperature extremes. This same principle could apply to exoplanets within the habitable zone, where water could create a buffer against the harsh fluctuations of an otherwise inhospitable environment. Moreover, water's solid, liquid, and gaseous states each play a unique role in shaping a planet's geology and atmosphere. Ice can carve landscapes, liquid water can erode and transport sediments, and water vapor can form clouds, influencing weather patterns and climate. Yet, water's role in habitability is not merely passive. It's an active participant in the geological processes that shape a planet's surface and atmosphere. On Earth, the water cycle is a critical component of the planet's climate system, driving weather patterns and redistributing heat. It's also a key player in the carbon cycle, helping to regulate atmospheric carbon dioxide levels and, by extension, global temperatures. In the search for Earth-like worlds, scientists look for evidence of these same dynamic processes, signs that water is not just present but actively shaping the planet's environment. Consider the icy moons of Jupiter and Saturn, where vast subsurface oceans lurk beneath thick crusts of ice. These oceans, heated by tidal forces and radioactive decay, could harbor hydrothermal vents, much like those found in Earth's deep oceans. These vents are oases of life, supporting complex ecosystems in the absence of sunlight. If similar processes are at work on exoplanets, they could create habitable environments in the most unexpected places. Thus, the role of water in habitability is not just about the presence of this vital ingredient, but also about the dynamic processes it drives, the environments it creates, and the life it might support. Biosignatures, searching for life. In the vast, cold expanse of space, the search for life beyond Earth has become a captivating endeavor, with scientists focusing on the detection of biosignatures, substances, or phenomena that indicate the presence of life. These biosignatures can be as subtle as a whisper in the cosmic noise, yet they hold the promise of revealing Earth-like worlds teeming with life. The journey to the habitable zone, where conditions might mirror those of our home planet, is fraught with challenges, but the potential rewards are immeasurable. Scientists are on the lookout for specific gases in exoplanet atmospheres, such as oxygen, methane, and nitrous oxide, which on Earth are predominantly produced by living organisms. These gases, when detected in the right concentrations and combinations, could hint at the presence of life, much like the lush greenery and bustling ecosystems of the Amazon rainforest. The search for biosignatures is not a straightforward task. It requires advanced technology and a deep understanding of planetary atmospheres. Telescopes like the James Webb Space Telescope, JWST, are equipped with spectrographs that can analyze the light passing through an exoplanet's atmosphere. This light, when broken down into its component wavelengths, reveals the chemical fingerprints of various gases. Think of it as a cosmic detective, piecing together clues from the faintest of signals. The presence of oxygen, for instance, is a strong indicator of life, as it is highly reactive and would not persist in an atmosphere without a continuous source, such as photosynthesis. Similarly, methane, which on Earth is produced by both biological and geological processes, could hint at life if detected in conjunction with other biosignatures. However, the interpretation of these signals is complex. False positives are a real concern, as some non-biological processes can also produce these gases. For example, volcanic activity can release methane, and certain chemical reactions in the atmosphere can produce oxygen. To mitigate these uncertainties, scientists look for multiple biosignatures and consider the context in which they are found. The presence of water vapor, for instance, is a crucial factor, as it is essential for life as we know it. The habitable zone, where liquid water can exist on the surface of a planet, is therefore a prime target for the search for biosignatures. This zone is not a fixed distance, but varies depending on the star's temperature and the planet's atmosphere. It's a delicate balance, much like the Goldilocks zone in our own solar system, where Earth sits just right for life to thrive. The search for biosignatures is not just about finding life. It's about understanding our place in the universe. It's a journey that combines the thrill of exploration with the rigor of scientific inquiry. As we venture deeper into the cosmos, the detection of biosignatures could herald a new era in our understanding of life, its origins, and its potential to exist beyond Earth. It's a journey that promises to be as awe-inspiring as the first sight of Earth from the moon, a moment that forever changed our perspective on our home planet. The search for biosignatures is a testament to human curiosity and our relentless pursuit of knowledge, a pursuit that could one day lead us to the shores of an alien world teeming with life. Technosignatures, detecting intelligent life. In the vast, silent expanse of space, humanity has begun to cast its gaze upon the stars, searching for signs of intelligent life. The concept of technosignatures has emerged as a promising avenue in this quest. Technosignatures are indirect signs of technology, much like how the presence of a campfire might indicate humans nearby, even if they are not immediately visible. These signs could range from artificial radio waves to atmospheric pollutants, or even the distinctive glow of city lights on a planet's night side. The search for technosignatures is a testament to human ingenuity, a high-stakes game of cosmic hide and seek. Consider the Earth as an analogy. From a distance, our planet's technosignatures might include the radio waves leaking into space, the glow of our cities, or even the unique chemical signatures of our industrial activities. These signs are not subtle. They are the unmistakable fingerprints of a technologically advanced civilization. Similarly, astronomers are scanning the habitable zones of other star systems, hoping to detect such telltale signs. The search is not easy. The cosmos is vast, and the signals we seek are faint, easily drowned out by the natural noise of the universe. Yet, with each technological advancement, our ability to detect these signs improves. The search for technosignatures is not limited to radio waves. Astronomers are also looking for signs of artificial megastructures, such as Dyson spheres, which could be constructed by advanced civilizations to harness the energy of their star. These structures would be detectable by their unique thermal signatures or by the dimming of starlight as they pass in front of their host star. Additionally, the study of exoplanet atmospheres could reveal signs of industrial activity, such as the presence of chlorofluorocarbons or other artificial chemicals. Each of these avenues offers a unique perspective, a different lens through which to view the cosmos and our place within it. The journey to the habitable zone is not just a physical voyage, but an intellectual one as well. It challenges us to think beyond our planet, to consider the possibilities of life beyond Earth. It pushes the boundaries of our technology and our understanding of the universe. And, perhaps most importantly, it reminds us of our shared humanity, of our collective curiosity, and our insatiable desire to explore. In the search for technosignatures, we are not just looking for signs of intelligent life. We are looking for a reflection of ourselves among the stars. The Fermi Paradox. Where is everybody? The cosmos is vast, a sprawling expanse of stars, galaxies, and planets that stretches far beyond human comprehension. Among these celestial bodies, Earth-like worlds nestled in the habitable zones of their respective stars hold particular intrigue. These are places where liquid water could exist, where temperatures might be just right for life as we know it to thrive. Yet, despite the high probability of such worlds existing, the universe seems eerily silent. This conundrum is at the heart of the Fermi Paradox. If the ingredients for life are common, why haven't we found any signs of intelligent life elsewhere? Consider the journey to one of these Earth-like exoplanets. A spacecraft, a technological marvel of human ingenuity, hurtles through the void. It's a journey that would take decades, even at the speed of light, which is an ultimate cosmic speed limit. Along the way, the spacecraft passes by gas giants with swirling storms larger than Earth, by icy moons with subsurface oceans, and by barren rocky worlds. Each of these is a testament to the diversity of planetary systems, a a reminder that while Earth-like worlds exist, they are just one piece of a complex puzzle. The silence from these worlds is deafening, a silence that echoes the questions posed by the Fermi Paradox. The paradox is named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" Given the high probability of extraterrestrial civilizations, why do we see no signs of them? One possible explanation is the Great Filter. This hypothesis suggests that there's some barrier that makes it difficult for life to emerge and evolve, or for civilizations to become advanced and detectable. It could be a flaw in the process of life's emergence, or perhaps civilizations inevitably destroy themselves before they can make contact. The Great Filter is a chilling thought, a reminder of the fragility of life and the uncertainty of our future. Another explanation is that we're alone, at least for now. The universe is unimaginably large, and the distances between stars are vast. Even if there are other civilizations out there, they might be too far away for us to detect or communicate with. It's like being in a vast, empty ocean. You might be surrounded by other ships, but if they're too far away, you'll never see them. This explanation is a humbling one, a reminder of our isolation in the cosmos. Yet, it's also a challenge, a call to explore and search for signs of life, to push the boundaries of our knowledge and understanding. The Fermi Paradox isn't just a question, it's a journey to the habitable zone and beyond. The Drake equation, estimating the odds. In the vast, dark ocean of space, the Drake equation serves as a beacon, guiding our understanding of the potential for life beyond Earth. It's a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way. Named after astronomer Frank Drake, it combines factors like the rate of star formation, the number of planets per star, and the fraction of those that could support life. It's a bit like trying to estimate the number of fish in the ocean by considering the size of the ocean, the number of fish per cubic meter, and the types of fish that can survive in those conditions. But instead of fish, we're considering intelligent, technologically advanced civilizations. The equation is often written as N equals R asterisk, FP, NE, FL, Phi, FC, L, where N is the number of civilizations with detectable electromagnetic emissions. R asterisk is the average rate of star formation. FP is the fraction of those stars that have planets. NE is the average number of planets that could support life per star that has planets. FL is the fraction of planets that could support life that actually develop life at some point. Phi is the fraction of life-bearing planets that develop intelligent life. FC is the fraction of civilizations that develop a technology that releases detectable signs of their existence into space. And L is the length of time such civilizations release detectable signals into space. It's a complex interplay of factors, each with its own uncertainties and variables. Consider our own solar system. We have one star, the Sun, and 8 planets. Only one, Earth, is known to support life. But we're not alone in the universe. There are billions of stars in the Milky Way, and many have planets. Some of these planets are in the habitable zone, where conditions could be right for life as we know it. The Drake equation helps us estimate how many of these planets might harbor life, and even intelligent life. It's a bit like looking at a vast, uncharted ocean and trying to estimate how many islands might be out there, each with its own unique ecosystem and potential for life. But instead of islands, we're considering exoplanets. And instead of ecosystems, we're considering entire civilizations. The Great Filter, a chilling possibility. In the vast, silent expanse of space, humanity's gaze is increasingly drawn to the habitable zone, that delicate band around stars where temperatures might allow for liquid water to exist. It's here, among the countless exoplanets, that we search for Earth-like worlds, places where life as we know it could potentially thrive. Yet, as we scan the cosmos, a chilling concept looms: the Great Filter. This hypothesis suggests that there's some barrier, some evolutionary hurdle that makes it difficult for life to emerge and evolve, or for intelligent life to become advanced and detectable. It's a sobering thought, a cosmic speed bump that could explain why, despite the high probability of life existing elsewhere, we haven't yet found it. Consider Earth's journey. From the primordial soup of organic molecules to the first simple cells, life on our planet faced numerous challenges. Each step, from the evolution of photosynthesis to the development of multicellular organisms, was a potential filter. Yet, life persisted and evolved. The Great Filter posits that somewhere along this journey, a barrier exists that is incredibly difficult to overcome. It could be behind us, explaining why life is rare. Or it could be ahead, a looming challenge that we, or any other intelligent species, may not survive. The latter is particularly unsettling, as it suggests that despite our advancements, we might be doomed to extinction before we can become a spacefaring, detectable civilization. The search for Earth-like worlds is, in part, a search for answers to the Great Filter. Each exoplanet we discover and study is a piece of the puzzle. Some worlds might be too hot, their atmospheres stripped away by stellar winds, a stark reminder of the fragility of habitability. Others might be too cold, their surfaces locked in ice, a silent testament to the challenges of maintaining a stable climate. Still, others might be in the right zone, their atmospheres hinting at the presence of life. Yet, even if we find signs of life, it might be simple, microbial life, a far cry from the complex, intelligent life we hope to find. Each discovery, or lack thereof, brings us closer to understanding the Great Filter, to understanding our place in the cosmos. As we venture forth, our spacecraft like modern-day arcs carrying our hopes and dreams, we must remember that the journey to the habitable zone is not just a physical one. It's a journey of understanding, a quest to unravel the mysteries of life and its place in the universe. The Great Filter is a chilling possibility, a reminder of the challenges that lie ahead. Yet, it's also an opportunity, a chance to understand our past, our present, and our future. In the end, the search for Earth-like worlds is a search for ourselves, for our destiny among the stars. Ethical considerations in the search for Earth-like worlds. The cosmos, a vast expanse of twinkling stars and swirling galaxies, has always beckoned humanity with its mysteries. Among these enigmas, the search for Earth-like worlds in the habitable zones of distant stars stands out, igniting both scientific curiosity and ethical dilemmas. These habitable zones, often likened to the Goldilocks zone, are regions around stars where conditions might be just right for liquid water to exist and potentially life as we know it. The journey to these worlds, propelled by advanced propulsion systems and fueled by human ingenuity, is not merely a scientific endeavor, but also a philosophical and ethical one. As spacecraft traverse the cosmic void, they carry with them the hopes and fears of humanity. The ethical considerations are as vast as the space they traverse. One of the primary concerns is the potential for contamination. Just as Earth's ecosystems are delicate and unique, so too might be the ecosystems of these distant worlds. The fear of introducing Earth-based microbes to these alien environments, a concept known as forward contamination, is a significant ethical hurdle. Conversely, there's also the risk of bringing back extraterrestrial microbes, a process called back contamination, which could pose a threat to Earth's biosphere. These concerns echo the historical lessons learned from the introduction of invasive species to new environments, often with devastating consequences. Moreover, the discovery of life, even in its most primitive forms, would raise profound ethical questions. How would humanity react to the knowledge that we are not alone? Would we seek to communicate, to interact, or to observe from a distance? The answers to these questions are not merely academic. They have real-world implications. The search for Earth-like worlds forces us to confront our own values and beliefs, challenging us to think critically about our place in the universe. It's a journey that requires not just advanced technology and scientific expertise, but also a deep sense of responsibility and ethical awareness. The cosmos, it seems, is not just a frontier to be explored, but a mirror reflecting our own humanity back at us. The future of human space exploration. The cosmos beckons, a vast expanse of stars and galaxies, each a potential cradle of life. Among these celestial bodies, Earth-like worlds nestled within the habitable zones of their respective stars hold particular promise for humanity's future. These planets, where conditions might allow for liquid water and a stable atmosphere, are the prime targets for our next giant leap. They are the cosmic oases that could one day quench humanity's thirst for exploration and survival beyond Earth. The journey to these worlds is not merely a scientific endeavor, but a testament to human ingenuity and our unyielding spirit of discovery. Picture a future where spacecraft, propelled by advanced ion drives or even fusion engines, traverse the void at a significant fraction of light speed. These vessels, designed for long-duration missions, would carry intrepid explorers and colonists to distant exoplanets. On board, rotating sections could simulate gravity, while advanced life support systems recycle air and water, much like the intricate ecosystems found in Earth's coral reefs. The journey would be arduous, but the destination, a planet with a blue sky and distant sun, would offer a new beginning. The technology to make this a reality is still in its infancy, but the path forward is illuminated by our understanding of physics and our ability to innovate. Upon arrival, these Earth-like worlds would present both familiar and alien landscapes. Volcanic activity, weather patterns, and geological features would shape the terrain, much like the forces that sculpted Earth over billions of years. The search for life would be a top priority, with scientists scanning for biosignatures in the atmosphere and exploring diverse ecosystems. The presence of even microbial life would revolutionize our understanding of biology and our place in the universe. Meanwhile, colonists would work to establish sustainable habitats, harnessing local resources and developing technologies to thrive in their new environment. The challenges would be immense, but the rewards, scientific, cultural, and existential, would be unparalleled. The future of human space exploration is not just about reaching these distant worlds, but also about what we learn along the way. Each mission would push the boundaries of our knowledge, testing the limits of human endurance and technological prowess. The data gathered would inform future missions, refining our strategies and improving our chances of success. Moreover, the journey itself would inspire generations, fostering a sense of unity and purpose. As we venture into the habitable zones of other stars, we carry with us the hopes and dreams of a species poised on the brink of a new era. The cosmos awaits, and with it, the promise of a future among the stars. As we conclude our journey through the cosmos, let's take a moment to soak in the wonders we've encountered. We've traversed the vast expanse of space, much like early explorers crossing uncharted oceans, to discover worlds that echo the familiar yet hold mysteries unique to their own environments. We've seen planets with years that last mere Earth days, and others where a single orbit around their star takes centuries. We've marveled at the dance of planets in the habitable zone, where temperatures could allow for liquid water, a key ingredient for life as we know it. Imagine standing on the surface of one of these Earth-like worlds. The sky might be a different hue, the gravity a different pull, but the sense of awe would be the same as when we gaze upon a sunset or a star-filled night sky here on Earth. These planets, like our own, are part of a grand cosmic experiment, a testament to the universe's boundless creativity. We've learned that the search for Earth-like worlds is not just about finding new places, but about understanding our own planet better. Each exoplanet we discover is a piece of a larger puzzle, a chance to see our home in a new light. The James Webb Space Telescope, with its advanced infrared capabilities, is our next great hope in this quest. It will allow us to peer into the atmospheres of these distant worlds, searching for signs of life and unraveling the secrets of their formation. So, as we sign off, we invite you to join us on this ongoing adventure. Keep looking up, keep wondering, and keep exploring. The universe is vast, and there's always more to discover. Who knows what incredible worlds await us just beyond the next star? Until our next journey, keep your eyes on the skies and your heart open to the wonders of the cosmos.